How do you solve problems in rotational dynamics? That's exactly what we're doing in this video. In the SI global measurement system used in science, angular acceleration is radians per second squared, torque is newtons times meters, and rotational inertia is kilograms times meters squared. Here's my 6-step framework for solving rotational dynamics problems, and it applies to pretty much 90% of these types of problems. Step 1, sketch the problem. This is optional. If the problem gives you a diagram, you don't need to sketch it. But visuals reduce 50% of the cognitive load. 2, your free body diagram. Analyze the forces. Step 3, identify all of the torques. Identify all of the torques and find the axis if you haven't already. 4, apply the second law, the rotation version. 5, if needed, we can use our kinematic equations, and you'll see why that matters. And 6, solve for your unknown. This works super well. And you might see this something similar in textbooks. But all we have to do is follow the steps. Let's go through our first example. You have a pulley. There's a cord wrapped around this pulley. The force pulling on this cord is 20 newtons. The pulley radius is 25 centimeters. And the mass of the pulley is 3 kilos. Why does the mass of the pulley matter? Because remember, rotational inertia depends on the mass. Let's say our pulley starts from rest and it accelerates rotationally to an angular speed of 40 radians per second over the course of 4 seconds. There's also frictional torque, which is acting against our rotation. This frictional torque is 1.5 Newton meters. Our goal, we need to find the moment of inertia, which is this. By the way, if you want all these formulas, they're on one cheat sheet in the description for free. Let's look at our problem-solving framework. We did our sketch already, so we can skip that. Now let's draw our free body diagram. So our pulley looks like this. This is the axis. This is the radius, which is 25 centimeters. We have the force of tension on the cord here. And we also have the force that's coming from the friction. Done. We have our free body diagram with all the forces happening. 3, torques and axis. We already know this is the axis. Let's look at the torque. So first of all, we have the torque coming from the tension, which is found with this formula. The radius is 0.25 meters, and we have 20 newtons of force, which was mentioned in the original problem setup. This is equal to 5 torque. The net torque would be all of the torque combined. So we have this torque of 5, and opposing it, so we have to subtract from it, is the torque of the friction, which was 1.5. So the net torque would be 3.5. Let's move this aside. Time for step 4, which is applying the rotation version of the second law. It looks something like this if you remember from our previous videos. There, do you see that? That's the moment of inertia that we're looking for. What do we have? We have net torque. We found it. And we're looking for this moment of inertia. But we also don't have angular acceleration yet. So before we get all happy and we find our moment of inertia, let's find angular acceleration. This is where step 5 comes in. We use our kinematics to find angular acceleration, which is 40 over 4 seconds, 10 radians per second squared. Now we can solve. So if we substitute in our values, we get 3.5 equals I times 10. Rearrange, put 10 on the other side. I is equal to 0.35. There we go. That's the moment of inertia for this pulley problem. All we had to do was trust the framework, and we got the result we wanted. How about a slightly more advanced problem? Imagine you're on the roof and you have a pulley that pulls up your toolbox. Here's some values. The toolbox weighs 25 newtons. It means the force of its weight is 25 newtons. So it weighs somewhere around 2.55 kilos. Anyway, this is tied to the cord of the pulley. The pulley itself has a mass of 4.5 kilos, a radius of 0.22 meters, and a frictional torque of 1.25 opposing our motion. The rope doesn't slip, it doesn't stretch, and we are tasked to find two things. The angular acceleration, so how fast it speeds up, and the linear acceleration of the toolbox, so how fast it gets pulled up. Our sketch is done, but we need a full body diagram. We have to choose and isolate our systems. There's two things happening here. We have the pulley itself, and we also have the toolbox climbing up. So let's draw two free body diagrams, starting with the first one, our pulley. So we have friction, torque acting this way. We have the radius, and we have the force of the tension of the cord this way. This here is the axis. Our second free body diagram is the diagram for the toolbox, and the toolbox is very simple. There's two forces acting on it. We have his weight pulling it down, and we have the force of tension pulling it up. So step 2 is done. What's next? Let's identify the torque. So the net torque for the pulley is the radius times the force of tension minus the torque of friction. That's the net force of the pulley. And also, Newton's second law in rotation form is net torque is equal to moment of inertia times angular acceleration. So that means net torque is equal to IA. Let's write that out and set that aside. And what we've done here is we set up a relationship between the torque and the angular acceleration, which is one of the things that we were looking for. Really, a lot of physics problem solving is finding a way to connect what you know, so the values you know, to what you don't know. Now, what's happening with the toolbox? We have the force of gravity minus the force of tension pulling it up. This is equal to MA, because remember, F equals MA. And we need to somehow relate this system to the pulley system. Because acceleration is also equal to radius times angular acceleration, we can substitute this in here and suddenly things connect. So let's go through step 6, which is solve. We can skip step 5. So this is going to be a big amount of solving. Let's make some space. If we move this to the other side and isolate tension, where Ft equals mg minus ma. And let's pull our other equation out. Let's take it out here. And we can substitute in this for the Ft here, which is R mg minus ma minus the torque of friction equals IA. And here, I want you to follow along as best as you can. It's going to get pretty math heavy. This is what we've been building up to. Let's expand this bracket. Yeah, Rmg minus Rma minus friction. If you remember, A is equal to R angular acceleration. So we can substitute that in. We get this. Rm times Ra. And that's equal to R squared times A. Now we need to bring all of the angular accelerations together. Okay, so I've went and moved this term to the right hand side. And here's where we're at now. I'm going to start making some space. We can factor out A, which gives us A I plus R squared M. And we can move this to the other side with division, and we get this. This is equal to A. I know that might have been tricky to follow along with. There's a lot of math, there's a lot of substitution, but it's a skill that you can practice. And the harder the problem, the more improvement you'll get if you're able to follow along. And by the way, every single value here, we can plug in something. Okay, I'm going to go and plug everything in. That is the angular acceleration for our pulley. That was a lot of stuff. And if you're wondering where we got the moment of inertia value from, simply use the formula. There might have been some rounding errors in here, but that's why we put the roughly symbol. We can find the linear acceleration of the toolbox because we have a formula that connects the two. Linear acceleration equals radius times angular acceleration. Radius, 0.22 times 18.3. Yeah, 4.03 meters per second squared. That's how fast the toolbox gets pulled up. So what we've done, we have found numbers that describe this pulley accelerating and speeding up while also pulling this toolbox up. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.